Okay, it's totally inhumane to give back a quest on the day you give a quest. But I really don't have. Did somebody lose flashcards? Did somebody lose flashcards? Or anybody who have? I've got flashcards 62 through 80 something. These are yours, just let me know. Okay, so you're this is how inhumane this is going to be. I would give back a quest, then I teach, and then you get another quest. There's nothing humane. If you're in the 90% club, meaning that you've always scored well into the 90s, you're like, bring it on, okay? But if you were like me, that would be like getting punched in the gut, being punched in the gut, getting punched in the gut again, and then getting punched in the gut a third time. So just say no. If I call your name and you don't want it, I will give it back next week. But those who want it can get it back. If you want to just not know, deal with it later, just say no, like drugs. Just say no. Okay, Luke. You want it? Sean, you want it? Stuart, you want it? Greer, you want it? Ava, you want it here? Now remember guys, you can just say no. Emily, you want it? Gordon. David. Jake. Ed. Roberto. Cameron. Will you separate that for me, Cameron? Brandon. Patrick. Brett. Josh. Zach. Stewart, right? Michael. Let's see. Hunter, you want this? Lizzie. Nick. Cosmo. Roberto. Sorry, Robert. Want it, Robert? Haley. Mason, you want this? Caitlin. Clayton. Sorry, Kaylin, sorry. Bridget, you want this? Rachel, you want it here? Alex? Okay, Alex. That was me. Another Alex. Caitlin. Oh, I wonder if I keep.
Yeah, this is Brandon.
Okay. Raylan. My eyes, Raylan, sorry. Michael. Alex. Okay, let's talk about these. The average in my one section was a minus 10.7, The average in my other section was a minus 10.2, So you have some sense of where you were for the average. That was a little high for this, material in general. The average is typically around a 69 out of 100, and this average was around a 77 to 75 out of 100. So that means you're getting it more than typical, or it just means that I'm getting weak in my old age. I don't know what it means. The high grade in my other class was a minus 0, which always pisses me off, because it means I'm not challenging my students. Then I had a minus 1/2, and then I had a minus 1.5. Then there were like 4 minus 2s, and a minus 2.5, and that was about where the highest scores were. But guys, this is Calc freaking 3, okay? You're in the 1% club. You're in the 1% club as far as where you're at. So like, if you're average on a middle school basketball team, okay, that's great, okay? But if you're average, on a Division I basketball team, is that okay? And if you're average in the 1% club, okay, is that okay? Let's Dr. Warren, you don't understand. I was the very best in my high school. No, you don't understand. Everybody around you was the very best in their high school. You're in the 1% club. Okay. I will put up the key. Why do I put up the key? Yeah, no, so you can make sure you're graded fairly and that see what you did wrong. Okay, do we test rockets before we fire rockets? I'm just wondering, should we test a rocket before we fire a rocket? Okay, why do we test it? Make sure it works, and if it's not working, what do? Fix it. We're abandoning the rocket, right? Okay, but we're going to do what with the rocket? Fix right. Look at guys, I'm not afraid to drink and grade. There's no rules against drinking and grading. Okay, I'm not afraid to have a glass of wine or 2 while I grade your things. Typically, the more wine I drink, the easier grading I be easier teacher. I'm like, oh, look at this poor sap, And then when I see like somebody miss all of the true and falses, I'm just like, oh, that poor child. I just need to tape a quarter to their test next time and just say, use the quarter. Heads, tails, heads. Remember, I'm the demon master when it comes to writing those things. Now you have what today? Another quest. So I'll put up the key. Not to this one today, but to the other one. Let me just tell you right now, there ain't gonna be any minus 0s. There ain't gonna be one. I'm not gonna be weak again. Everybody gets challenged. I'm sick and tired of not curving myself. Okay, I want to make sure you've got 40 minutes to take this beast. So, is that clock even close to right? Not bad. Okay. So what time does class end? 11. So if I give you 40 minutes, what time should I start you? 10:20. So if I'm not done here in like 20 minutes, you've got to throw something at me, Robert. okay? You got it, so let me know, okay? Okay. I worked really hard, and you did too. You're still on the edge of not understanding differentiability in higher dimensions. How many people recognize they're on the edge of not understanding differentiability in higher dimensions? Okay, so, oh, you mean on the edge? Dr. Warren, I'm completely over the edge of not understanding. Okay, math is proof. So, I just can't believe I'm recording and I just said I drink it great. What kind of an idiot am I? Okay, we have a different definition of differentiability, true or false? Then you're totally not on the edge, you're gone, okay? Do we have an edge? Do we have an edge? Do we have a definition of differentiability? Okay, we say that a function, a two-dimensional function, and for just notation purposes, I'll use the vector. We have a multi-dimensional function, and we say it's differentiable. And last time we kind of just used 2, 3, which I almost go interchangeably between the point and the vector. The function is differentiable at 2, 3, if and only if what? You're like, well, how has everything been defined in calculus? How has everything up to now been defined in calculus? Limit. So it's not shocking that our definition of derivative in higher dimensions would also be defined in terms of a limit. If and only if there exists a vector d, which is, we're thinking of it as the derivative. Now, because we're two-dimensional, it's going to have two components, such that the limit as x approaches 2, 3, as x approaches 2, 3, now it's not shocking at all that there would be division in a derivative definition. True or false? True or false? The sad thing is that our limit is a vector going to a vector. So, and there is no such thing as vector division in Gibbs's vector calculus. So we avoid that by putting, instead of dealing with the vector, we deal with the norm, and in the bottom we've got an x minus a, or x minus 2, 3 in this case. Now, as x goes to 2, 3, where does the norm of x minus 2, 3 go? Dr. Warren, I'm not focused. As x goes to 2, 3, where does the norm of x minus 2, 3 go?
0.
0, which is just what we would expect, in a definition of derivative. In the numerator, we would expect a what? If you're thinking about the limit as x approaches a, in the bottom you got your x minus a, what would you expect in the numerator? F of x minus f of a, and that's what we've got. We've got this f of x minus my f of a, which I'll just call 2, 3. But because of the norm, and because we can't divide, norms are always positive, true or false. Norms are always greater than or equal to 0. There's this punishment for having to deal with the norm that we've got to actually deal with an absolute value up there. To do any work, to make any progress, we've got to have that absolute value. And this limit doesn't equal d. This limit doesn't equal d, again, because of the norm and the absolute value. The limit's equal to 0. It's up in here where my derivative is. And we have this d dotted with, because d is a vector. Notice scalar, scalar, scalar. This is going to have to be a what when it's all said and done? This is going to have to be a what?
Scalar.
Scalar. And we're going to have this dot product x minus 2, 3. X minus a. Now what I did last time was I worked really, really hard running the limit along 2 domain curves. If the limit's going to exist, what did I just say? Say that again. And it does exist, and it's the number 0, then the limit along every domain curve has also got to go to 0. Okay, so I had these 2 domain curves. They weren't very clever. one domain curve, call it C1, was R of t was equal to 2t. My other domain curve C2 was R of t was equal to T3. Now I draw you, if I draw you, right, draw. So let's just draw an x, y, z. This is the which axis, this is the which axis, this is which axis? X. Y. Now my interesting point in the domain is, is 2, 3. So mark yourself a 2, 3 on what you just drew. Give yourself a 2, 3. So there's my point down in the domain that I'm taking my limit towards. Now if this is going to be a domain curve, there has to be a C. There has to be a C that I plug into it that hits the point 2, 3. There has to be a C that I plug into it and hits the point 2, 3. And what is that C? If you're just looking at it, what would the C have to be in this domain curve to hit that point 2, 3? 3. And how about that domain curve? What would it be? 2. And so if I was going to, how many people think you may be running along domain curves on this next quest? I mean, the one you're going to take in just a little bit. How many think that might be, if your hands aren't in the air, you didn't study. Just like, okay. So if I'm running this thing along this domain curve, wherever I see the x, I'm going to put a r of t. In the x coordinate, I would put the 2, and the y coordinate, I'd put a. Okay, if I'm running along this domain curve, where in the x coordinate, I'd put a. And on the y coordinate, I'd put a. But in this case, I'd be running my limit in the C2. If I'm running along C2, I'd take the limit as t approaches, as 2. And if I'm running along C1, it'd be the limit as t approaches 3. And that's what we did. And when all the smoke cleared, we came up with these two amazing results. That my vector d1 and d2, the components of my derivative, ended up being, now read that to me. I want to see how you're doing in reading. This represents the derivative with respect to, now say partial derivative with respect to x. Say that. Which means we're going to treat y as, in application, you're going to treat y as a constant. If you take the partial derivative of f with respect to x and plug the number 2, 3 in, that's what d1 was. That number is d1. A vector is an order triple of 3 real numbers. In this case, because I'm two-dimensional, it's going to be an order double of 2 real numbers. The first real number is that one. And then what did we find the second real number to be? It's not hard. Just go ahead. You guys are good at extrapolation. F sub y at 2, 3. I mean, I just have to let you know that they're sending Secret Service agents to Delaware. They're no longer allowed to fly over Joe Biden's house. So if you're wondering how the election's going, that's a pretty good sign that they're sending Secret Service agents. So our election's coming to an end. So you can just focus today on your quest, okay? You don't need to worry about the election. You need to focus on your quest, okay? So here we go. The first component, how do you get the first component of the derivative? Partial derivative of f with respect to, and you plug in the two numbers, 2 and 3. In the x, you would plug in the 2, in the y, you turn in the. How many people think they can do that? If I gave you a space curve, how many people think they could, a space sheet, how many people think they could do that? To get the second value of the derivative, you take the partial derivative with respect to, and plug in the numbers 2 and 3. So this vector d, my derivative vector, the first component is, and it's right there for you. The first component is, if I make you write it down, you might remember it. F sub x evaluated at, and then f sub y evaluated at. Now through history, they don't call it the derivative. Historically, they don't call this vector the derivative. They use the word derivative for one dimension. So they got to give this thing a name, and they call it the gradient. And it gets worse. They have a symbol for this derivative, which we're now going to call the gradient. The symbol for this d, well, they know that it changes as f changes, true or false. The derivative is going to depend on the function, true or false. So they use this symbol. It's like a vector. They call it the gradient symbol. They put an f here, which means it's the gradient of f. And then they put the 2, 3 there. But guys, this just means d. This just means d. So they have that symbol. How many people have seen that symbol before? Okay, if you get in physics, if you get in PChem, if you get involved in any kind of engineering, eventually you're going to run into your gradient. But don't be panicked. It's just the partial derivatives. Okay. Now stand up. Don't breathe on anybody. Stand up. Stretch. Okay, sit back down. Robert, what time are you hitting me? Okay. Okay, Luke, if he fails, you've got it, right? Okay. If not, let's see, who do I actually absolutely trust that would throw something at me? Yeah, okay, Nick would have me. Okay, all right. You're not gonna like this. We've now got to run the limit, not along a nice easy curve like this. This is just a freaking line. Or this, which is also a line. What I want you to do is I want you to draw an arbitrary domain curve. So make it curvy. Draw an arbitrary domain curve in your drawing that goes to the point 2, 3. Just draw yourself an arbitrary domain curve that goes to the point 2, 3. And I'll do the same thing. I'll make it curvy looking. Does that work for you guys? Now I'm just going to, for lack of anything better, I'm going to call this curve C3. And I'm just going to keep it as R of t. It's a curve that's running down here. Since it's a domain curve, there has to exist a C where R of C actually slams into that point. So R of C would actually be equal to the vector. Vector 2, 3. I know that RC is actually equal to the vector 2, 3. I feel so MIT-ish every time I do that. You guys are at MIT now. Except I'm nothing like a professor at MIT. Sorry, back to where we were. How many people are with me? How many people are with me? Now, how many people realize Dr. Warren's not going to write this thing down all over again? How many people recognize Dr. Warren's not going to do that? I'm going to get really lazy. I want to run my limit along this. I want to run this limit along this arbitrary domain curve. I want to run this limit along this arbitrary domain curve. Is it a domain curve? Is it down here, and does it actually hit the point that we're interested in? Then the limit along this curve has to be equal to what? The limit along this curve, if I run the same limit along this curve, what does the resulting value have to be if the limit actually exists? Do this. Look around the room. What does the limit have to be? David, you're not doing it. 0. Look around the room. Say, do not score a 0 on the quest. Say that. So if I'm looking at this, I'm going to run this along this domain curve, which is this symbol. We would say it's the limit as x approaches 2, 3 along the domain curve, C3. Air quotes means lazy. That means Dr. Warren's not going to write this down all over again. Dr. Warren's not going to write this down all over again. I guess I should probably, for you guys, just state it here, even though we're not going to use this in the next couple minutes. That we're really talking about a vector valued function where you have an x of t and a y of t. It so happened over here, my x of t was the constant too. My y of t is just the simple t, and vice versa there. This could be really complicated functions of x and t. Now imagine that you're running this along a domain curve like you might be doing in just a couple minutes. Then wherever you would see an x, you would put your x of t, and wherever you would see the y, you would put your y of t. And this would be equal to the limit as t approaches, I erased it. The limit as t approaches c. The limit as t approaches c. Now we're going to end with this. Wherever I see the x, I'm going to put my space curve r of t. So I would have the absolute value of f of r of t minus f of 2, 3. So that's not changing. Where else do you see an x in the numerator? So here I would put a r of t. Do we know what d is now? Do we know what the vector d is now? Like, Dr. Warren, I don't know. We don't know. Do we know what the vector d is now? It's the, use your new vocab word, it's the gradient evaluated at 2, 3. So we know what that is. I'm not writing a gradient, I'm just leaving it as d because I'm lazy. Dotted with, now what would I put there? R of t minus the vector 2, 3. Now we're almost done. We've got a norm down here, and so this would be R of t minus the vector 2. Okay. How many people are following so far? And then, you guys held your hands up just a moment ago. This limit, because the limit exists, has to go to what value? This limit, because the limit exists, has to go to what value? 0. Now to give you a hint where we're going, 2, 3 is the same thing as, and I'm helping you, I'm pointing to a line. 2, 3 is the same thing as R of C. So wherever I see C, the vector 2, 3, I could substitute in a R of C, which would give me an R of C here and an R of C there. Okay. If you want to figure out where we're going, it's just like a bad nighttime soap opera. It stops right at the most interesting point. Stops right at the most interesting point. And then we go to a brand new show. But on Monday, we'll pick up with this. Okay, but right now you could start a new episode of Quest. Okay, Quest. In fact, which episode is this? The 4th episode of Quest. Okay, make sure you put your names on this. Just keep passing stuff backwards and we'll pick up the, get extra copies, just keep loading them back. Some down to Cosmo. You got one Cosmo there?